Cool. Thank you very much, and thanks for putting this together, Jimmy. So yeah, I'm Jim. The protocol team, we just work on open source stuff in the crypto space. So we just contribute to projects like Bitcoin Core. And the reason I'm talking about this is I've been contributing on and off to one of the major Lightning implementations, LND, for the past 8 months or so. So this is going to be a fairly technical talk. We're going to break down the protocol specification that specifies how Lightning Network nodes communicate with each other. It's an 11-part spec. There's 11 bolts, and so we're going to go kind of piece by piece, bolt by bolt. Some of them will be more in depth than others. I want to I know people are probably at different levels of understanding with this stuff, so can I just kind of pull, who knows what a UTXO is? Okay, great. Who knows what an HTLC is? Great. Okay, cool. That's helpful for me to know where to spend time and stuff. Okay, very high level. What is a blockchain? It's an ordered transaction ledger, and the kind of defining properties, in my opinion, are that it's globally replicated. Computers around the world are constantly synchronizing these transactions with one another. You have this notion of probabilistic finality, which means that a single computer, when it's downloading the ledger, at some point in time can make an assessment and say, I am almost 100% certain that this transaction will never be reverted from the global state. This idea of probabilistic finality is really important. And it's censorship resistant, which means that if you are trying to make a transaction and you're willing to pay the fees, it doesn't matter what the contents of the transaction are, it will make it into the ledger eventually. So these are the properties. In this talk, we'll be talking about the Bitcoin blockchain, but these are kind of general properties of blockchains. And what this gives you on the plus side is zero counterparty risk. So if I send you $1 million today, you know, and you wait 30 minutes, you know absolutely that you have this $1 million and there's no way for it to be reversed, even if, regardless of how much you trust me or don't trust me. And that's kind of all the good things about blockchains. They have a lot of downsides. Because they're globally replicated, they're really slow. It's expensive for everyone to run these things, and you have pretty poor privacy by and large because everything's public. Everyone can see every transaction. So when we think about how people have solved transaction efficiency in the past, if you think about how our financial system works, there's kind of batching at every layer. So if I make some bank transfers, those don't hit the Fed account balances immediately. All the banks batch up all of the transactions they're going to do between one another once a day. So all the transactions between banks get batched into once a day, and you don't even make bank transfers for most things. You pay with a credit card and then settle your credit card bill once a month. And then there are certain things like opening a tab at a bar where you don't even want to do a credit card charge for every transaction. So at every layer we have batching, and that's what the Lightning Network tries to provide. So we're going to drill into that last example of the bar tab. That's going to be kind of this constant analogy we have. So Alice is at Bob's bar. They don't know each other, and they're both pretty paranoid people, so they want every assurance at every step of no default. So Alice opens this tab, and she gives Bob an IOU, and she's going to sign this and say, I owe you $5, and Bob gives her back a beer. And then they do another transaction, and instead of giving him another IOU, she's going to kind of replace the old IOU. So she writes a new IOU, signs that one for $10, and says this one replaces the old one. And now Bob's willing to give her another beer, and then hopefully at the end of this interaction, they will settle up, and Alice is going to pay Bob the total balance of the IOUs. But as I said, Bob's pretty paranoid. What if Alice doesn't pay? So he kind of, he could ask for the money up front, but Alice doesn't want to give him the money up front because what if he doesn't refund? So they try to find some mutually trusted party. We're going to go with this guy, Dorian. And they both trust this guy, and he's going to hold the money in escrow. So the very first thing that happens when Alice opens the bar tab is she gives $20 to Dorian, and now she can do up to $20 worth of beer. So we do the exact same thing. She buys a few beers, she gives some IOUs, and then Bob at the end of this can just give the IOU to Dorian, and he sees that it's signed by Alice, and he can divvy up the original settlement, so he gives $10 to each of them. And this is pretty good, but we don't get any guarantee that that Bob is actually going to give Alice a beer after she pays, or she gives him an IOU. That exchange of the IOU for the beer isn't really atomic, and it never really can be unless you do some physical thing. But we can, pretty surprisingly, do atomic swaps of payments for receipts, for signed receipts that a payment was delivered. And so the way we do this is Bob's going to sign this sort of message that says, if Alice knows this SHA-256 pre-image, then she must have paid me $5. Like, I know this pre-image, and I'm only going to tell her if she pays me. So Bob's going to sign this sort of notice, and then Alice is going to construct this contract that says, if Bob reveals the pre-image by 1 p.m., I'm going to pay him $5. And so this contract on the right, super important. It's called an HTLC. It's the building block of a lot of this stuff. And this is how we're going to do these atomic swaps of payments for receipts. So instead of giving Bob an IOU, she's going to give him an HTLC. And this has to be parameterized with the hash, the amount, and the expiration. Those are the parameters to this contract. It's a binding contract. And now Bob can give Alice the beer because he knows the pre-image, and he knows that at any time he can go and take the signed HTLC, the signed contract, and give it to Dorian along with the pre-image, and this together constitutes proof of, it fulfills the contract. Oh, I put $10. It should be $5 and $15. So Dorian will pay out, but this is like kind of inconvenient because if Bob presents the HTLC right now, he only has until 1 p.m. to do that. And so that means Alice's bar tab has to close out by 1 p.m. So there's another thing they can do. Since Bob knows he can do this at any time, what he's going to do is when Alice gives him the HTLC, he's just going to tell her the pre-image right away. And now that Alice knows the pre-image, she has this receipt, the signed receipt from Bob that says, I've been paid for beer. So she's going to replace the HTLC with an IOU, because at this point, he has the money and she has the proof. And so now the tab remains open past 1 p.m., and they can continue transacting. OK, so the analogy is going to break down at this point. We have this abstraction, this way for people to pay each other back and forth once they've established this initial payment to some escrow person. And so what we want to figure out what we can do is how can Alice pay Bob if they've never opened a channel with one another? Everything that I called a tab before is now going to be a channel. So she wants to establish this payment system. I, Alice, will pay you $5.50 if and only if you pay Bob $5. So I'm going to give you a 50-cent fee if you can facilitate this payment to Bob. But I want it to be, very like an if and only if. Like, you don't receive money unless you pay Bob. So Alice gives an HTLC to Carol for $5.50, and she's going to delay it a little bit. The expiration is going to be 1:15. And what Carol can do is if she gives an HTLC to Bob, she knows that if she has to pay Bob, she has the pre-image that she can turn around and give back to Alice. So, and Bob in this case has received, payment for his beer, so he's willing to give the beer to Alice. And sort of the whole interaction, I don't show it here, is going to play in reverse, where Bob gives the pre-image to Carol. Carol now has a nice 15-minute buffer to turn around and give that pre-image back to Alice, or if she needs to, go to Dorian and sort of settle and close out that tab. So this is how we're going to chain these channels together. And sort of this is the fundamental insight behind the Lightning Network. And this whole interaction that I've sort of described is, for the remainder of the talk, what we're going to break down the protocol that sort of actually instantiates this. just a little bit of history. A lot of these ideas are really old. In fact, Satoshi, in early emails with devs like Mike Hearn, talked about the idea of batching and using payment channels, but we didn't, in Bitcoin, have the technology, or we didn't have the right features in the scripting language for a while to do it. But in 2013, core devs, Matt Corral and Mike Hearn, they actually wrote a payment channel implementation. It was broken, but and they knew it, but it was there. And then in 2015, the Lightning Network paper got released. This had a few major kind of landmarked findings. One was the ability to do bidirectional channels. So if, if Alice pays Bob some money, she doesn't need to open another channel for him to pay her back. They can use the same channel to pay back and forth with this Lightning Network construction. And it kind of came up with this idea of using HTLCs to chain these payments together. In 2016, these three teams that were kind of separately working on Lightning at the time decided to get together and come up with an interoperable specification so that all of their implementations could work with one another, and that's called the Bolt spec, and that's what we'll be talking about. And it took, we're kind of just at the point where these things are getting launched into beta. 2 of the 3 are approved for mainnet usage. They're all getting used on mainnet at this point. I think why I wanted to put the timeline up was it takes a really long time to get this stuff right, essentially. And we're kind of just at the cusp of this stuff being usable. So without further ado, we're going to start right at the beginning at Bolt 3. So this is how you actually construct the smart contracts. Out of curiosity, how interested are people in kind of Bitcoin minutia? Because there's like a lot of it, and I plan to skip it, but okay. If you have questions, ask. I feel like this stuff is pretty Bitcoin-y and also kind of subject to change. There's even a new proposal to overhaul a lot of this, but here's the basic ideas. The very first thing that happens when you open a channel is one participant creates a transaction paying to a 2 of 2 multi-sig address. So you have 2 endpoints. They swap public keys with each other, and one of them pays to a contract that says the only way to spend this money is with explicit authorization from both endpoints. And that's it. This goes on blockchain. This gets confirmed. This is how the channel opens. It's non-malleable for reasons that are important, and we'll talk about in a second. And then in the optimistic case, they do a whole bunch of back and forth payments, the whole bar thing with the HTLCs, blah, blah, blah. And then in the optimistic case, all that happens is they mutually agree, okay, the division is now Alice gets 75% of the money and Bob gets the other 25, and we'll make a transaction that pays out in those proportions to the 2 of them. We will both sign this because we agree that's how it should be, and this goes on chain. So in the mutual consent case, this is the only interaction that anyone sees. It's a multi-sig spend. But this is the very last transaction to be agreed upon between the 2 of them. Now, the whole time, so if we look at this, why would Alice pay to a 2 of 2 multi-sig if she knows that maybe Bob is going to go offline and there's no way for her to ever spend these funds? That would be really bad. She needs some way to ensure that she can get reimbursed. So the entire time, both endpoints, Alice and Bob, are going to keep what's called a commitment transaction. And the commitment transaction is something that they store on their own, and if they need to, because the other party stops cooperating or they come into disagreement or whatever, they always have the option of publishing this transaction on chain. And so each node has a separate commitment transaction that's signed by the other node before anything happens. And you're probably confused because this transaction looks just like the closing transaction, but I'm telling you they're different. The reason is because one of these outputs is encumbered by an additional condition that makes it safe so that there's this challenge period. So what we want to do is if Alice publishes this commitment transaction, we want to give Bob a a time buffer, let's say a day, to see that this happened on chain and say, okay, this actually was the last state that we agreed upon and not some prior commitment transaction that I gave her a long time ago and was reverted. So, you know, if in some state Alice has 75% of the money and then she pays him a little bit more and now she only has 50%, we need a time buffer so that if she publishes the transaction where she has more money, Bob can go and challenge it and say that's invalid. This was actually a replaced state that Alice said she was never going to broadcast. So, ooh, this is kind of small. Okay, so what we do essentially is the direct payment back to the person who publishes the commitment transaction has two different ways to spend it. One is after a time delay. If you have signatures from both parties, then it goes to the person it's intended for. So if I publish and I wait 10 minutes from the time, or sorry, like a day from the time that I publish, then I can get my money back. Within that day, though, there's a non-time restricted clause that says, if Bob has this sort of trapdoor key, this secret revocation key, then he can spend at any time. And so the way we're going to enforce that people don't publish past states, that they only publish the current state of our negotiation, is by saying if you ever publish a last state, you're going to have to give me a trapdoor key up front that allows me to spend everything. It allows me to take the entire channel balance. So it's really never in your interest to publish a past state because I'm going to punish you by taking all your money. So these outputs are encumbered by this time delay. So the commitment transaction, though, doesn't just have the two outputs. It has all these HTLCs. So we can encode HTLCs in Bitcoin script. And some of the HTLCs are from one person to the other. Some are from the other person back to you. What an HTLC typically looks like is it has two redeem clauses. If you're curious, this is a language called Ivy, which compiles to Bitcoin script. And I know you can't read it, but I think it's more readable than Bitcoin script. An HTLC has two clauses. One says, if you have the preimage, so if Alice is giving an HTLC to Bob, then Bob can spend it with the preimage, or Alice can spend it after the time delay. Those are the two clauses, the timeout and redeem. So we have a problem if we just put these right in the commitment transaction directly. The problem is that we have parameterized the HTLC by one timeout. This is the expiration time on the HTLC agreement. But we also have another timeout, which is this challenge period. And so we can't really put both of these timeouts into the same contract, into the same Bitcoin script. So what we do is we have to break it out into two separate layers of transactions. Sorry, I want to elaborate on that a bit more. So if Alice publishes this commitment transaction, and one of the clauses is Bob's going to pay me if I have a hash preimage. On the one hand, she shouldn't be able to spend that immediately and get the money because it could be an old state, and that would be bad if she could get the money immediately. But she also needs to immediately lock in the fact that she has the preimage before that HTLC times out. So when she publishes the commitment transactions, she's going to immediately spend the HTLC, but it can only be spent to one place. It can only be spent to these pre-signed transactions called the HTLC success timeouts. And this is where the challenge delay happens. So we have this, the commitment transaction is actually a whole suite of commitment transactions. You have one kind of base transaction, and then for every HTLC, you have a separate, the second layer of transactions. Does that make sense? Why there are two? Yeah. The trapdoor is on all of these outputs, but after the challenge period expires, the trapdoor is still there, but the other person should have swept the funds at that point. So it's kind of a race. As soon as the challenge period ends, like they're racing, but like really there should be no race because you should have just done it before. But that brings us to a good point about these trapdoor keys. They're called the revocation keys. we're going to have a series of these commitments, right? Every time there's a new state, there's a new commitment. And it would be bad if they all had the same trapdoor key, obviously, because if you got it once, then you would have it for all future transactions. So the revocation key needs to be different for every commitment transaction. And actually, we want all of the keys. There were like 5 different keys up here, and this is like a simplified version of it. We want all of the keys and all of the scripts to be different on every transaction. There's a reason it's better for privacy if you want to use a watchtower. I'm not going to explain that. So what you do is instead of when you open a channel, you don't tell the other person a key. You tell them an elliptic curve point that they use to derive all of the keys. Who knows what like BIP32 is, the hierarchical wallets? In a similar sense, you can use one private key to derive a whole bunch of future private keys. And so up front, they just exchange something that they use to derive all of the future keys for all of the future transactions. And that's how you get different revocation keys. OK, Bolt 5 specifies on-chain handling. It's pretty simple. So both of these endpoints have this channel open, and they're both watching the blockchain at all times. If someone spends the funding output, they know immediately to check, is this the latest state? Then, OK, we'll let it happen. We'll just close the channel. If it's a past state, then go use your revocation key and steal all the money. That's pretty obvious. The other case where you actually want to take your commitment transaction and publish it on-chain immediately, maybe the other person's just like totally negligent and you need your money now, you could do that. But also if you have an HTLC that's like about to expire and you have the pre-image, you should definitely publish that commitment transaction before the HTLC expires so that you can spend it with the pre-image before they time it out. And then conversely, if you have a timeout, if your HTLC just timed out, you want to publish the transaction so you can spend the timeout clause. So if any of your HTLCs are getting close to the expiration, you publish the commitment transaction now. And that means the other party just like was misbehaving because they should have done something at that point. And then, I mean, Bolt 5 has a whole bunch of other rules, but it all just boils down to like anything you can spend, like spend. Like if you have a pre-image, spend. If your output timed out, spend it. Just sweep everything all the time. Cool. So this brings us to the protocol itself. So every Lightning Network node is connected to the Bitcoin network. It's monitoring the blockchain, but it's also connected to the Lightning Network, which is a totally separate peer-to-peer network. And so there's a bunch of just typical peer-to-peer stuff that you need to know, like how are they communicating? Well, they're communicating over TCP. What's the serialization format? Custom binary serialization. There's a few other like cool things about the handshake. So the protocol is pretty extensible. When you connect to someone, you give them a bit field of all of the features that you support. So let's say, for example, let's say we wanted to upgrade one of those transaction formats and we decided, oh, there's a better way of writing this script. Do you support this new way of writing the script? Well, you advertise that when you connect to someone. There's another cool rule that I want to talk about that I just think is clever. There's this general over the entire protocol, it's OK to be odd rule, which means that in many situations where things are numbered, even numbers mean like odd numbers are optional features. So every protocol message has a number. Like the hello would be 1, and then some of the messages we'll see in a sec might be 5 or 7 or whatever. Well, they should all be even. Any protocol message that's odd, you will ignore from your peer if you don't know what it is. Any protocol message that's even that you don't know what it is, you're going to disconnect immediately. So it kind of bakes in extensibility in kind of a neat way where, and in these feature bits, I said like there's this bit field. If your peer has a feature that's odd that you don't know, you'll kind of let it be. If they have a feature bit that's even that you don't know, you'll disconnect. So kind of just a neat way of doing extensibility. OK, and then we do encryption and authentication over this TCP connection with this protocol called noise sec p256k1 cha-cha poly sha-256. That's probably enough, right? So what this actually means is like instead of using TLS or something like that, this is kind of a more lightweight way of doing what TLS does, but like with far fewer dependencies. So with TLS, you basically need OpenSSL, which is something that people don't really like to include if avoidable. And also it brings in some cryptography that is sort of non-native. What Lightning does is it uses the same exact elliptic curve that Bitcoin uses. So you use the same dependency, and it has a really fast stream cipher. This is all basically to say that it's got a really kind of lightweight and modern way of doing encryption and authentication. Importantly, this means that every connection is authenticated. So when you connect to a node, you have their public key, and there's no way that you could be man in the middle. You know you're going to authenticate that they have the private key. So every node has a cryptographic identity on the network, unlike in Bitcoin, where you just connect to like a host and port, and like you hope that, in fact, you don't even care if they're who they say they are. So that's the difference. Okay, now we can get into kind of what I think is the most interesting part of this and what I'm going to spend the most time on, which is how do we take that whole bar protocol, that interperson protocol, and turn that into like network messages. So yeah, this is basically what we want to replicate. So Alice and Bob, dotted lines are TCP connections. They have a TCP connection, and Alice wants to open a channel. And right now, Lightning only supports single Thunder channels, so Alice is basically going to tell Bob, hey, I want to open a channel to you. I'm going to pay for everything, so like it's at no cost to you. Like, do you want to accept this channel? And she's going to give him some parameters, like this is the most I want to have in flight, like in HTLCs at any time in terms of money. Like this is the amount of time that you need to wait to get your money back, right? There was like that challenge period. Like there's a bunch of parameters to these channels that they need to negotiate up front. So Alice asks Bob, do you want to accept this channel? Bob says, yeah, I want to accept the channel. Here are my parameters. Alice is going to locally create the funding transaction herself. And she's not going to tell that transaction to Bob, but she's going to tell him what to sign. So that the initial commitment transaction that just does a full refund back to Alice of the entire amount that she's putting into the channel, he's going to sign that because there's no reason not to. He doesn't need to put up any money at this point. So Alice creates this transaction. She says, here's my signature, and give me yours. So he signs back. And then she can fund this transaction and publish it to the blockchain. And they're both watching the chain. When it confirms, they send this funding lock message, which means like our channel is open, like let's go. And dashed lines are channels. Okay, so this is where it gets interesting. So the first thing Alice is going to do is send HTLCs to Bob. And these are numerically ordered just sequentially from 1. So every time Alice gives Bob a new HTLC, new number. And these are all parameterized with the HTLC parameters. And then at the end of like a bunch of updates, she gives this commitment signed message to Bob. So she doesn't actually give him the commitment transaction. She just gives him these signatures. Because Bob can locally recreate the commitment transaction himself based on the history of their messages. So they're not actually exchanging transactions. They're just exchanging sufficient information to recreate these transactions. So Bob knows, OK, I know how much went into the channel, and I know these HTLCs, so this is what my transaction is going to look like. And do Alice's signatures actually sign this? So he's going to check the signatures. And if this is all good, then he's going to send back a revoke an ACK message, which essentially it acts that I've received your signatures and I think they're good. And it revokes the prior state, saying, OK, not only have I acted that your signatures are good, but I will never publish anything before this state ever again. And to ensure that, here's my revocation key for the past state. So he actually gives back that revocation key so that we talked about, it's like this trapdoor key. Alice can go and spend it, his prior state, if he ever were to publish that. So at this point, Bob still can't go and like give Alice the preimage. Why? Because he's revoked his past state, but Alice hasn't revoked her past state. So she actually still has a valid state in which these HTLCs didn't exist. So what has to happen now, Bob has to send back a commitment signed and say, here, you go and update your view of the state. Here's my signatures on it, and Alice is going to send back revoke and act. So these two changes, the HTLC add, have been signed by Alice and act by Bob, and signed by Bob and act by Alice. And when we're in this state where this change has been applied in both people's state and all prior states are revoked, this is called, these updates have been irrevocably committed to the channel state. And this is important because once the HTLC is irrevocably committed, Bob can respond. So he can say, I'm going to take the money on HTLC 1. Here's the preimage. So like, I'm going to fulfill this HTLC. And then the HTLC 2, like, I don't know, maybe the amount was wrong, or actually like you got the destination wrong and I don't know how to fulfill this, or expired, or whatever. I'm going to fail this one. So this basically says I'm going to claim the first one and I'm going to reject the second one. And these are new updates that have to happen. So Bob's going to go ahead and apply these to his commitment transaction, sign that new transaction, and then Alice is going to act it, and then Alice is going to take those two updates, and she's going to sign the new commitment state with those applied. Bob's going to act it, and now the fail and the fulfill have been irrevocably committed to the channel state. What did I want to say here? OK, any questions about that stuff so far? Yes? Yeah, I mean, this is just as fast as you can send messages over a TCP connection. Yeah. I think, so, OK, sorry. It's as fast as you can send stuff over a TCP connection, but you need to persist the signatures. So that slows things down. That's the slowest part of this, because like Bob, you know, if Alice revokes a thing and gives him the revocation key and he doesn't save that to disk, like he's in a dangerous position. So you have I/O, disk I/O happening. So that's kind of what slows some of these interactions down. But yeah, it still happens like way under a second. OK, so far this whole interaction, oh, sorry, the other thing I meant to say here was the sender of the HTLC always sends the HTLC add, and the recipient of the HTLC always removes it. So let's say Alice sends Bob an HTLC that times out after a little bit. Alice has no way of telling Bob, like, hey, let's clear this timed out one from the transaction. It's Bob's responsibility. That just simplifies the protocol. So like the sender of the HTLC adds it to the state, and then the recipient removes it from the state. The other thing about this whole interaction has been that it's been one direction, Alice to Bob the whole time. But actually, this is bidirectional, and it's happening bidirectionally, like simultaneously. So Alice sends two HTLCs to Bob. Bob sends two HTLCs to Alice. You can see like the IDs, the incrementing IDs, are in different namespaces for the two different directions and increment on different counters. And when we get down here, like, what is Alice signing? Because we don't really know if she's even received these from Bob yet. Like maybe she has, maybe she hasn't. So how do we make sure that it's like unambiguous what she's signing, right? So there's this essentially, hopefully this example shows us, but when you send a commitment signature, you're only signing the updates that you sent. And then the revoke is how you sort of link these two logs together. So this stuff gets really confusing. This is like why I wanted to put it up, because it's like a total mind bender, but it's going to be fun. OK, so Alice has a view of the updates that she sent to Bob, and she has a view of the updates she's received from Bob. Sorry, give me a sec. Bob also has a view of the updates he's received from Alice, and he has a view of the updates he's sent to Alice, right? And these are these can be out of sync because it's an asynchronous TCP connection, but they will happen in the same order. So Alice creates these two ads, and right now she just has them, and then she sends them to Bob, and then Bob gets them. So they both have the same sort of like view of their interaction, and then Bob's gonna do an HTLC ad and send that to Alice, and simultaneously Alice is gonna sign her two previous ads, and then she's gonna send the SIG to Bob. So she is only signing the stuff in her column, right? Oh man, you can't see the colors. This is, okay, well, these are yellow for now. That's a bummer. Okay, so she sends the commit sig to Bob, but these haven't been acked. So these are kind of in a pending state where Alice has signed it, but it's not irrevocably committed yet, right? And then she receives the HTLC ad from Bob. Bob gets the commit sig. He's gonna send this ACK. So he sends the ACK. It's still not irrevocably committed on his side because Alice hasn't acked a change in which, or Alice hasn't revoked the prior state where these HTLCs didn't exist. And then simultaneously, Alice is going to add another HTLC. So yeah, this gets confusing. The purpose here is like these things are all happening simultaneously, and they will come into consensus with each other due to the way these messages are constructed. So then what happens? So Alice receives Bob's ACK, and as soon as she receives Bob's ACK, let's see, she's going to immediately, what happened there? Oh, Bob got the ad and he got the SIG. She gets the SIG from Bob. Nothing really changes, except that she's gonna ACK the commit. So let's see. So let's go back here. So this commit, this commits to the add, but it also commits to the revoke. So this, you can kind of follow this up and then down this line. So this commit means I've added this HTLC for myself, but I've also received your two ads. And so that means it's irrevocably committed in Bob's view because he's signed this state. And then, so he sends that over. And then as soon as Alice acts this commit, then it's irrevocable. Sorry, it wasn't irrevocably committed yet. Now it's irrevocably committed in Alice's view because she has revoked the state before these two ads were added, right? And then as soon as Bob gets it, those went green, which means that this was irrevocably committed. So the only thing that's been irrevocably committed at this point is these two and these two, and then those two are in a pending state. And so as soon as Alice sends the revoke, she also needs to send a SIG. So this is now signing the fact that I've revoked, or like this kind of signs this stuff, and it signs this. And what happened there? Oh, now because Alice had irrevocably committed this one, Bob's going to go and fulfill HTLC 1. And then he's going to sign that. So again, still the only thing that's been irrevocably committed so far is the two ads from Alice. He gets the commit sig, and then they both revoke. So what's been committed now? Let's see. So Alice's update, she's acked this stuff. This is still incomplete because this needs to be acked by Bob as well, which we get, no, over there. Fuck. This got really confusing without the colors. So anyway, this stuff works. Yeah, routing protocol. So, okay, we've got these ads, and then we need a way of chaining this stuff together. So every ad packet, I said it had the amount, the ID, the expiration, and the hash. It also has another field, which is a routing packet. So the routing packet actually has the entire information for the whole circuit. So if Alice sends a packet to Carol, that packet says, here, add this HTLC, but also here's Bob, and like here's maybe David behind Bob as well. And so for every hop, you need to tell them, okay, what's the next channel in the hop? What is the amount they're supposed to get, because each one has a fee, and then what's the expiration time on the HTLC, so that everyone unambiguously knows how to construct the packet that they're supposed to send out. But this kind of leaks a lot of information, right? Because now Carol knows not only how much money Bob's getting, but that he's the last person in the entire channel, that Alice is the first person in the whole circuit, that Alice is paying Bob. So it turns out we can encrypt this stuff using onion routing, which is the same technique that Tor uses, where every hop only sees the next hop. So, and every hop behind that is encrypted. So if you look at what the packet looks like, it looks like, you know, I have my hop information, I have like my information that I'm supposed to forward on to the next person, but everything after that is encrypted to the next hop. So when the person at hop 1 gets this packet, he's going to decrypt this, and then he sees hop 2, and he can forward it on. And what's really cool about onion encryption is not only do you kind of hide the amount that is ultimately transacted down the line, but you hide who the ultimate sender is and who the ultimate recipient is. So if you just see the next hop, you don't know if that next hop is the ultimate destination or whether they're forwarding it to someone else. So you've kind of added a really interesting layer of privacy to these payments. You can glean certain information, like if you know roughly in the range of what people are charging for fees and you know the network graph, you can try to deobfuscate some stuff, but it's a privacy enhancing technique. And we can do this because every node has this public key bound to their identity. That was the authentication key when we talked about the noise protocol. Not only is routing information encrypted, but if there's a problem, like the recipient has to fail this for some reason, not everyone back upstream sees that error. That error is encrypted back to the original sender. So we get some pretty good privacy properties from this. Anything else I wanted to say? No. Okay, so now we have a way that if the sender can create this routing packet for the entire circuit, then we have a way for everyone to pay each other and for people to forward payments. So now all we need is a way for people to discover routes. And so if we have this network where all these people are connected by channels, at all times, everyone's just gossiping about who they have channels with, as long as both of them opt into that channel being public. And so they're all constantly synchronizing this. And so not anyone has like a global view in a consistent way of the topology. Like this node might only know about these 4 other nodes and these channels between them. But then eventually, hopefully, as these nodes come online and they gossip, and like this person tells this person, he's going to relay the information about this channel over to the original person. So eventually this stuff should synchronize, and ideally everyone does have a complete view of the entire network graph. So with the entire view of the network graph, you can construct your own routes. That does put a pretty large burden in terms of bandwidth and storage and stuff and memory usage on every node as the network grows. That's just how the routing works right now. So there's 2 kind of main packets that are interesting in this gossip protocol. So first you announce a channel. This happens once, and you say, here's the output on the blockchain. This is really important because, one, it allows people to tell whether your channel is still open and whether they should continue. Like if that funding output didn't exist, then that channel doesn't exist and there's no reason you can stop sending payments through it. but it also tells you the amount, the total capacity of the channel. And that doesn't need to be explicitly put in there. And the channel announcement is signed by both endpoints. And then every side of the channel sends these channel updates at all times. So this is one side of the channel signs this and says, hey, like maybe the other person went offline, so I just want to like tell the world I'm not going to be able to send payments right now, so I'm going to disable this channel. And then when they come back online, like I'll send a new update that says, okay, they're back online, channel re-enabled. You can also say like, if you're going to route through me, like this is the fee I'm charging, and maybe that you want to change that dynamically over time. Every time you change the fee, you propagate out a new channel update message that gets propagated through the network. So if people were doing that all the time, it would cause a lot of bandwidth consumption. And every channel update has a timestamp so you know what the latest one is. So let's see. Yeah. Oh, you can prune old channels. So like if you don't get a newer update for a channel within some period, I think it's like a few days by default, you'll just kind of drop that channel. And so if you have a channel, you're supposed to rebroadcast a channel update every so often. OK, this is the last one, I promise. So Bolt 11. So kind of it ties everything together. What does an end-to-end payment look like? Well, oh, I thought it looks like this, I guess. So if you want to pay someone on Lightning, they're going to give you a blob that looks like this. And you can tell because it says LNBC. This is the amount. It's 2,500 micro Bitcoin. And then there's a whole bunch of other data. And you can take this, it's Bech32 encoded, and you can decode it, and you can see your Lightning software should be able to tell you, OK, the recipient has this pub key, so go find them on the network. The amount is 2,500 micro Bitcoin. It expires in 60 seconds, so pay it before then. Here's the hash, and you can put a description in. So this is really cool because it does kind of this half of the receipt thing, right? So if you have a signed invoice by the recipient that says, if you have this pre-image, then like you have for sure paid for this item. That's a really powerful thing where the pre-image combined with the Lightning endpoint, the Lightning invoice, together forms irrefutable cryptographic proof of payment. Let's see. Anything else I want to say about that? No. OK, so this is going to be demo time in which I do a demo with a script that I hacked together this afternoon that like very well might not work, but we'll try it anyway. Give me a sec. This is an app called satoshis.place, and if you go and visit it on your own, be aware that it's like quite not safe for work, but I've managed to find a spot that seems to be for now. So I've got a script that should, crap, you can't really see my screen. Let's try this. I'm just going to talk really loudly while I do this. So on the left, this is my Lightning node. It's not really doing anything at the moment, but so I've got this one channel open. It happens to be to Satoshi's place, but like theoretically you could connect to someone who's connected to Satoshi's place. But I want to make sure it's reliable. And on this script that's going to interact with the Satoshi's place API and tell it that I want to put something at location. is my Lightning invoice. So if I decode the invoice, the software tells me all the things I said. So there's an amount, there's an expiry, I'm paying for 200 pixels if Satoshi's placed, and keep your fingers crossed. Cool. So we got the hash created. So I paid him. Oh, shoot. I forgot to change the script. If you want to watch for another second while I undo something. One more time. And this is on mainnet. So now, hey, we got it. All right. Who has questions? Oh, this is the Grateful Dead symbol. Yeah. Yeah, I've got it on my shirt too. Anyone else? What are you spending? Okay. Let me go back. Sorry, I know it's probably like not that helpful for me to pull this up, but I think it will be. So this is a one input, two output transaction. So if Alice is the funder, she pays from anywhere, but it actually should be SegWit inputs or else this whole thing isn't secure because malleability. So it's a one input transaction, like doesn't even matter where that came from. Doesn't even matter if you have change. You could like open 5 channels at once. What matters is that it has this one funding output, the multi-sig output. So any transaction that a funder could construct that has a multi-sig output, that as long as the multi-sig output was established using parameters from that initial handshake, that's a valid interaction. So if you're closing, it just looks like a 2 of 2 multi-sig spend. It just, you put a Bitcoin in the channel, there's a 0.3 output, there's a 0.7 output, just looks like a spend from a 2 of 2 multi-sig. If you go into the weird cases, so what you'll see is, okay, you've got this commitment transaction. You're going to see a pay to witness script hash thing. So this looks like it looks like a SegWit output, but when it gets spent, it's going to have a clause. Sorry, this isn't Bitcoin script, but it actually it does compile to Bitcoin script, and it's going to have like an op-if, and it's going to say actually I had another tab up that has it, but essentially you'll see some weird custom scripts, and you'll be able to know like, oh, this is a Lightning payment. Like you'll see that. You'll see, oh, it has this redeem clause with a local delay, and there's these different keys. And then the HTLCs have their own format, and so I said like, this HTLC only pays to this one. Well, the reason is because it actually takes a 2 of 2 multisig to spend this, and from both Alice and Bob. And when they sign the commitment transaction, they sign a 2 of 2 multisig on this output, and they also sign a 2 of 2 multisig on each of these outputs. Does that answer the question? Or? Yeah. Yes, so actually there's like 3 conditions for all of these. So, okay, if we look at this output, it has 2 conditions. It's spend after timeout or revocation. If we look at this output, there's 3 conditions. It's one is a pre-image reveal to the other person. The other is a timeout with a timeout clause to this transaction, and the third is a revocation to wherever the person with the revocation key has it. And then these also have the revocation key. So basically every output along here has an op-if clause for the revocation key thing. If you are interested in what like the specific script formats look like, you can look at Bolt 3. Hopefully that helps.
Thank you.
Yeah.
Compact client-side block filtering in terms of block clients.
Like this is what I work on most of the time. I really like this stuff. Timeline. So, okay, the original BIP draft got published like last summer, which is when Lalu started talking about it and stuff. I kind of polished up the BIP in December, and that's when it got a number. And unfortunately, the BIP itself didn't really get review until I wrote some pull requests in core, and that sort of like put the heat on the people in core who want to review stuff to actually go and review it. So basically, if you follow the mailing list, there's been a huge round of review where the BIP kind of got overhauled. I hope this stuff makes it in soon. There's 2 layers to it. I just put out some blog posts the other day if you're interested in reading relevant stuff. But you know, initially we'll do this peer commitment thing where you have a lower amount of security, and I still think works pretty well. That kind of got the peer commitment stuff. It works less well as a result of the most recent round of review, but it still kind of works. And then I think it's a year or and a half at least until we see block commitments.
Yeah, because I know the problem with like my clients right now, like how like running Neutrino on your mobile phone doesn't really make sense. So I'm playing around with similar questions myself.
Cool. Let's talk afterwards. Right, sorry, let's pull that up. So you're talking about this stuff, right? So let's go all the way down to here. It really would be nice if we had these colors. But so when Bob fulfills this, let's see. What does he? No, he's gotten, he's done a commit sig that, He's done a commit sig where this revoked, this revoked this. At what point? Oh, sorry. He sent this revocation on this commit sig, and then Alice sent this revoke. So this revoked the state prior to these getting added. So this covers both of these 2 HTLCs. So when he does the fulfill for 1, he could have done the fulfill for 1 and 2, or he could have failed 2, or whatever. What he can't do at this point is fulfill 3, even though if we fast forward a little bit, well, like so Alice sent this at HTLC 3, and then she revoked something like that. Didn't do anything to this HTLC3. So at this point where he does the fulfill one, like he may have learned about this, but that's not irrevocably committed. Or with one or two, yeah. Right, so now she commits the HTLC and then, and then she revoke acts, and then he has to revoke act, and now it's irrevocably committed. Yeah.
I think we got time for like one more, so.
No. In the current spec, no, but the routing packet has I think it's called a realm byte, so it's extensible in the sense that like there's, I think, 1,300 some bytes blocked out for routing information, and right now the only defined format that you can put in there is the onion routing format, but I'm pretty sure the realm byte would apply with the it's okay to be odd rule. Oh, good example of that. So if you defined a realm byte that's odd, then, well, actually no. But you could enable a new feature bit that says like, hey, I support this like new routing format, and it would work in the protocol. It's just people would need to know how to parse that routing thing. So you could go and define your own routing spec if you wanted to like remove the onion routing or actually just do like so one thing I didn't talk about with the onion routing, this is like very different from how like the internet works with BGP and stuff. With that, you tell your ISP the destination, and they, you know, use their routing tables to figure out like who the next person they should send it to is. So if you wanted to construct a Lightning routing protocol like that, you can do it within the message formats, but you need to define that semantic yourself.